では、時間になりましたので、第何回だったかな、52回ですね。順番がね、52回の ASE 研究会を始めたいと思います。東京大学の下川辺です。よろしくお願いいたします。はい。Anyway, okay, we'll now start the 52nd ASE seminar, and this seminar will focus on the topic related to the utilization of the machine learning for the simulations. So we have the two talks in this seminar, and the first one is the speaker is Natalie Kubicki from the University of Cologne, Germany. And the second speaker is Yuki Nagai, Professor Yuki Nagai from the University of Tokyo. Okay, so let's move on the first talk. So the first talk, the title is investigating the feasibility of the convolutional neural network surrogate model employing overlapping domain decomposition approach for the steady state blood flow prediction. And the speaker is Natalie Kubicki from the University of Cologne. And please join me in welcoming Natalie.
Thank you so much for the kind introduction. Today I will give you some insights about my the research I did here in this short-term research stay in the group of Kengo Nakajima and Takashi Shimokawabe. It's a joint collaboration between our group from the University of Cologne, comprising Axel Clavon, Martin Lanzan, Janine Weber, and Simon Claes. And I will start with motivating our research, then move on to the models and method used. Then in the third part, I will tell you something about the work we've done in the past weeks and a conclusion and future outlook. So the motivation is basically that computational fluid dynamics simulations are widely used in many engineering tasks, such as automotive design. And steady state flow problems, where the material flow properties does not change over time anymore, are a potent tool to assess the flow dynamics. And they are simulated by solving systems of partial differential equations, which can provide accurate results, but are also computationally expensive. And what we would like is, especially for early design stages, or in general, is rapid feedback instead of obtaining results after a few hours or days or months. So we would like to develop surrogate models. And one such approach, convolutional neural networks, which have been successfully applied to steady-state flow predictions in the past, for example, by Xiao et al., which is also the ground base for Shimokawabe's work. And the initial idea would be to say, okay, we have a global domain, and this is our input image for the convolutional neural network. So the problem which may arise is, first, for accurate predictions, we need a large amount of data, so we need to do many simulations. Also, what if we have really big domains, we could get memory constraint problems. And keeping in mind that for each new geometry, we have to do some kind of retraining. So instead of thinking about the global domain as an image, Shimokawa and his student Hatayama introduced a boundary exchange method based on or inspired by an overlapping domain decomposition approach, where we train the convolutional neural network on smaller subdomains extracted from the global domain. And this also helps by the CNN to learn on these local subdomains, which are kind of easier problems to learn. And then in the prediction phase, an overlapping domain decomposition approach is used to exchange boundary information between neighboring subdomains. And the hope is that if the local CNN predictions are accurate enough, the global prediction should converge to the global solution. And this is kind of schematically visualized here. So in their work, they looked at such kind of problem, where they used lattice-Boltzmann simulations as simulation data, and then they extracted first a global domain from a larger lattice-Boltzmann simulation, and set at all global boundaries, Dirichlet boundary conditions. And now instead of treating this global domain as an input image, they decomposed overlapping subdomains, trained the CNN on the single subdomains, and then use in the prediction phase kind of a red-black scheme, where we divide into even and odd numbered subdomains. And we first predict the even numbered subdomains. We then obtain in the overlap region a new prediction for then the next step, the odd numbered subdomains, which they get as an initial input. And then they do the odd numbered subdomains do a prediction, and basically we then, in this kind of iterative manner, we exchange boundary information and hopefully we converge to the global solution. And this was already implemented and tested, and with this toy problem showed that it works. The idea was now to implement or to apply this method to a more realistic example of a stenosed artery blood flow. So the idea is to have CFD simulations for blood flow using patient-specific data, and hopefully in the future with from arteries from medical imaging. And again, the CFD simulation are accurate, but also for longer artery section or even networks, they are computationally expensive. So again, we could use this idea to dividing the global domain into consecutive overlapping subdomains to train locally fast CNN surrogate models. And this could be kind of this idea of decomposing this domain into local overlapping subdomains. And now for my 10-week stay here, the idea was that, we wanted to conceptualize and train a CNN-based surrogate model for first 2D blood flow for simplicity in stenosed artery, applying an overlapping domain decomposition prediction approach. And the three main tasks were the generation of the training data, training the CNN surrogate model, and also look at the results. And basically, this was the time plan which we hold onto. So in the first week's generation of training data, then also the post-processing to obtain input data for the CNN, training, performance and evaluation, and then further improvements and final presentation. And now I want to dive more into the models and methods, and it's subdivided into the CFD part and the neural network part. So first the CFD part. So as our ground base for this neural network is the simulation data, we want to have realistic data. And for blood flow, there are many different approaches and numerical methods to simulate blood on different length and time scales. And our group at the University of Cologne is looking into macroscopic models, where we use radiological constitutive models in a finite element framework to simulate the blood flow. And our partner group at the Forschungszentrum Jülich, a Forschungszentrum in Germany located, they are doing simulations really on the micro level, where they use particle-based models capturing the interaction of all the red blood cells for more realistic fluid simulation. And what they can provide us is really so they can really under concrete condition, they can generate us viscosity data for the blood. So we have known material properties. So the model equations on the macroscopic equation then look like this. We have the assumption that we have a single phase, homogeneous, isothermal, stationary, incompressible, generalized Newtonian fluid. Generalized Newtonian is the difference between the Newtonian fluid, that the viscosity is now no longer constant, but we have a shear thinning assumption. So the viscosity changes with the shear rate. And this is physically correct for blood, as due to the high volume fraction of red blood cells, they have an effect on the overall radiological properties, and it shows a shear thinning behavior. And equations are then the mass balance and the momentum balance with Dirichlet boundary conditions and a Newman boundary condition at the outlet. And the only difference to the classical Navier-Stokes equation lies in the shear stress tensor part, where we now have the non-constant viscosity function. So this is a continuous nonlinear problem, as in form of a coupled nonlinear system of PDEs, which we first discretize using finite element method in order to obtain a discrete nonlinear problem. And the nonlinear problem, we then have to linearize using, for example, Picard iteration or Newton's method in order to obtain a discrete linear problem, which you then can solve. And our group solved it using a preconditioned GMR solver, leveraging two-level overlapping Schwarz methods, where the global domain is decomposed into local subproblems, and we can really efficiently solve in parallel the problem. So the software environment I want to quickly introduce is our in-house code FATLib, stands for Finite Element and Domain Decomposition Library, and is built up on the open source software Trilinus, where we leverage from nonlinear solver packages or a parallel distribution of matrices and vector operations. And the most important package is the FOSH package, which stands for Fast, Robust, Overlapping Schwarz Preconditioners, where we can really use the parallel scalable overlapping Schwarz domain decomposition preconditioners for our model problem. So, and the whole problem on the macroscopic scale to obtain the blood simulation data is then first, our partner group can generate using their mesoscopic methods viscosity data under certain conditions for a specified volume percentage of red blood cells, for a specified temperature, for a specific red blood cell mechanics, and they can give us that, and they give us then data, which is viscosity independent of shear rate. Then this can fit into a curve, and we can use it in our macroscopic simulation to simulate blood using this specific data. So now we know the way how to generate realistic blood flow simulation data. So now, instead of using the simulation approaches, we want to train a surrogate model, a CNN-based surrogate model that approximates the solution operator, and which maps from an image with width and height, with a certain width and height, to another output image. And following the approaches of the previous work done here, we use as 3 channels as an input. So assigned distance field, which gives us geometry informations, and boundary velocities for the X and Y component. And I will introduce this notation on the next slide. And the output of the CNN should be then the velocity X component and the velocity Y component in all the pixel grids. Additionally, mask is applied to ensure that only at the no slip boundaries and outside of the geometry, the velocities are set to 0. We will later also see. So if we now have a global domain, which would be indicated here by this outer frame, we would first split it into overlapping subdomains, indicated here with a certain overlapping width. And then the CNN is trained on each of the overlapping subdomain images, where each of the subdomain has a resolution of 256 pixels in width and 128 pixels in height. And yeah, this would be our ground base for the CNN training. And now to introduce this notation of this boundary velocity input, it is here visualized. Basically, we say that inside of the domain or in a certain region, these values are 0, and we only extract at a certain region at the right or left boundary velocity informations. And if this psi, this is now the input red width, is equals to 1, if we would just extract information at the left and right boundary, but it can also be bigger than 1, and then we would extract in a certain kind of boundary region velocity informations. But this is defined as being smaller than the overlap width. So, and now the original approach from Shimo Kawabe, which I now call Takashi approach, was that the input red width is equals to the overlap width. So for obtaining the boundary velocity input, the velocity information are read in this whole 2 stripes at the left and right boundaries. And the prediction of the CNN is then on the whole subdomain. So also the boundary values are overwritten. We discussed it then also with my supervisors from the University of Cologne. And coming from the classical alternating Schwarz proof, it is known that basically for the global convergence proof, Dirichlet boundary condition has to be set on the subdomains. So this is needed for the convergence proof. And inspired by that, we thought about a different approach where we first think that, okay, the input red width is now just at the left and right boundary, and the prediction is only done inside, and we hard enforce the boundary conditions. So this is the difference. So then we could think about, so this is really inspired by partial differential equations where we only can have like at the boundaries informations, but we are using CNNs. So we can use kind of a combination of Takashi's approach and the classical alternating Schwarz approach and call it hybrid approach, where we now extract boundary informations in this certain regime to give more information to the CNN and hopefully get a better output prediction. But again, we hard enforce the input boundaries information in the output. So these are basically the three approaches, where the hybrid approach for the input width equals to 1 is just the classical alternating Schwarz approach. This is now the network architecture, which was already implemented, visualized, where we have our input image, which has the size as had been previously, and 3 channels, sign distance field, and the boundary velocity x and y component. And then we use kind of convolutional operators with certain activation function, a flatten layer, and then 2 separate deconvolution paths to obtain the velocity x component and y component. And here we see the application of the mask in order to ensure that the output outside of the geometry and at the boundaries is really 0. This is maybe later also better visualized. And if we now train the CNN for this single subdomains, this would be now for the prediction phase, the algorithm for the red-black boundary exchange method. And the first step, we would have a new global domain. We would need to compute the signed distance field. And for this global domain, the boundary velocity input. Then we would split the global domain into overlapping subdomains with a certain overlap width. And then we would divide them in even and odd numbered subdomains. We would do first for the even numbered subdomains using the trained CNN in the local domains, a prediction to obtain new predictions in the subdomains. Then as an intermediate step, we would override the global inlet and outlet. And then the odd numbered subdomains would use informations obtained by the even numbered subdomains previously to obtain a new prediction in their subdomains. And then we would get after the iteration, we would get for the whole domain a prediction. And this would run until the current minus the previous prediction in the L2 norm is smaller than a certain threshold. So it does not change anymore too much. I also now want to visualize it. So this would be the visualization of Takashi's approach and the hybrid approach. So we first would have like the global grid, and we would extract velocity boundary informations here for Takashi's approach in a whole region equals to the overlap width. And in the hybrid approach, only because we set here this input red width to 1/2 of the overlap width in a smaller part. Then we would first look at the even numbered subdomains, and they would extract boundary velocity informations. So here they would have already information. This would be 0 in the first step. It's here the same. And then the even numbered subdomains would do a prediction. So they would do the CNN would be evaluated. And for Takashi's approach, we now predict in the whole domain, whereas here we set hard enforce the boundary conditions. So this is the difference. Now this would be the intermediate step where we again set global inlet and outlet, so known global inlet and outlet values. This would be for this approach not necessary as we set the boundary conditions, but it's still visualized. Then the odd numbered subdomains would obtain new informations for producing a prediction. Then again, the global inlet and outlet would be set to certain values, and then we would do another iteration. Okay, so this was basically all the methodology. Now to the workflow, which we implemented in the last few weeks. So basically, it's divided into 3 steps: the pre-processing, so the generation of training data, which we divided into mesh generation, simulation, and post-processing to obtain the input data. Then the training and the post-processing in terms of visualization and discussion of the results. And the entire pipeline, including all needed subrepositories, is currently stored in a private GitHub repository, and all the computationally were executed on a Vestaria supercomputer using the Aquarius nodes, simply because it was easier to install all the necessary libraries on the using the Intel compiler. So this was as a start to not waste so much time. So the mesh generation is now, we need it for our simulation environment, we need unstructured meshes. So if we first use a PyG mesh and MATLAB to obtain meshes in our required mesh format, where we have for all meshes now the assumption that we have a maximum diameter of 1 millimeter. The total length is equal to 2.4 centimeter, and then the inlet and outlet region are 0.7 centimeter long. And in the intermediate mesh, there is now a varying number of stenosis sections. It can be between 1 and 3, and it can either be symmetric or asymmetric as a stenosis section. And they do not have always the same relatively length. So in this case, it's really optimized. So we just have to set a certain number, and then the code gives us hundreds of different kind of geometries, which we can use for simulation. And currently, it's a number of elements per mesh, 114,000. So then these meshes can be used in our environment also automatically. We just need to give it as an input, where we then obtain as an output H5 simulation data files of the velocities, pressure, boundary flags, and also viscosities. So you first only use the velocities, but basically all the other data we also can obtain. And the model assumptions are that the density is constant, and it's 1,000. It's a fixed viscosity function, so it's non-constant, but it's fixed. So the parameters are fixed for a certain hematoxid value, so a certain volume percentage of red blood cells, certain red blood cell mechanics, which are known. No slip condition at upper and lower walls, Newman outlet condition, and a parabolic inflow velocity profile was set, where we vary the maximum velocity between 0 and 0.6. These are a bit more the simulation details, where we each simulation took about 5 minutes using 1 node of Aquarius with up to 36 MPI processes. And the simulation results now look, for example, like this, where we have a certain first channel flow, then the stenotic part where flow is accelerated, deaccelerated, and again a channel flow part. And what we already see is that the dominating velocity component is the x velocity, because in these channel parts, the y component is 0. And also in this part, it's smaller, depending on the geometry. But basically, what we know is that in a certain at the input and at the output, the velocities are actually the same, because it's just a developed profile. So that's why we can use in the CNN approach, we can use directly boundary conditions for the velocity not only at the inlet, but also at the outlet. So it's because we made the assumption that the outlet is long enough, and we have also a developed flow at the outlet. It was just for first initially to maybe help the global CNN approach to converge, because if not, we would just have information at the inlet, and we would have to propagate the information through the whole channel. So we thought about maybe it's helpful to have outlet informations. So the next step would be then to now do a post-processing step in order to generate the pixel grids, because now it's defined on unstructured meshes. So we now use our in-house VTK Python-based code to sample the velocity data and the signed distance field data on a pixel grid. And then from each simulation, we extract 14 sub-images of this kind of size. Where we use 9 subdomains over this whole regime, and additionally 5 extra sub-images only in the complex region part. And the signed distance field we also compute in this kind of post-processing step by just saying we look at the minimum of the distances of one point from to the upper or lower wall and assign the signed distance field value to the minimum of one of these values. And that's kind we obtain information about the geometry. And at the upper and lower boundary, this value is 0, and also outside the geometry. And based on this signed distance field, we can also compute the mask, which is needed in the convolutional neural network to set the velocities to 0 outside and at the upper and lower boundary. So now we have everything which we need. So in the training of CNN model, there are many experimental variables. Some I fixed, so this where you see, so we have a data set size of approximately 4,000 images. It's not too much, but we started with this. Then a data split ratio in training test validation data, 80%, 10%, and 10% validation data, a certain learning rate, and more assumptions. I won't go into detail because we can discuss later. And the metrics we look at is the train, test, validation loss, and also for a specific grid, how the prediction is on the local subdomain and how the prediction is performed in the global domain decomposition approach. So basically, we would want to do it for all the grids, but now for visualization and discussing, I show only the results for one specific grid. And now we start with the Takashi approach, where we set a certain overlap width, which is here 8. And we know there is also the input width is the same. We have a mean squared error function as loss function. And what we see is that the training process converges to a train test validation loss after 300 epochs to the 10 to the power of -5. And it takes 30 minutes to train, only the train step. And the prediction on the subdomains you will see now are good, but the domain decomposition approach does not converge. So first, the subdomain prediction. Now, for a certain subdomain, we use this trained CNN model, and we already see for the X component, it quite looks good. So here's the prediction, the ground truth, the absolute error, the relative error for X and Y component. So we already can see here, due to the nature of the problem that the Y component is much smaller, or even like going to 0, it's much harder to learn. So that's why the Y component is not so good learned. But if we look at the mean squared error between prediction and target, it's small. It's in the region of 10 to the power -6 or 7. If we look at for another subdomain, it also looks good. So these are just visually, but it already looks good for this case. But now, if we use it in the domain decomposition loop, so this would be now the global solution of the problem, where you saw before, like only the first subdomain and this subdomain. Now we look at in the global approach, and we would start with only velocity values at the inlet and outlet. Inside it's 0. But this would be one approach, but we kind of use the knowledge that we already know that the mean flow rate is constant throughout the cross sections. So we don't have to use as initialization for inner subdomains 0. We can also set a parabolic profile with the same mean flow rate in order to give already better starting values for the CNN. And we saw that it's not, so if you initialize with 0 or with a certain parabolic profile, it converges to the same solution. So it just accelerates the convergence behavior. But what we now see is after approximately 120 iterations, the L2 error stagnates with in a certain value, and we see it converges to a wrong solution. So although the predictions for the individual subdomains were relatively accurate, the global solution did not converge. So now let's look at the classical Schwarz approach, where we say the input ref width is only at the inlet and boundary outlets, so only in this one pixel layer. And yeah, this approach I showed you before. So again, the training converges. And what we now see is that in the prediction of a local subdomain, we have a slightly over prediction. We see in the next slide. But the domain decomposition approach converges. So we see here now, these are for one local subdomain, and it's not perfectly seen, but this is kind of slightly over predicted, which is also seen in this absolute error. This is a larger error than before. Also for this subdomain. And what we now see is that although it converges after 200 iterations to a third, it converges with a certain error, it converges to a wrong solution. And this is due to the fact that in the subdomains, it is locally slightly over-predicted. So let's look at the last approach, the hybrid approach, where we now set an input red width to 8 and an overlap width to 10. So because we already saw previously that in the Takashi approach with an input red width 8, we got good local predictions. I hoped to obtain also good local predictions using the same input red width. But what we here now saw is that it showed a weak under prediction. So here again, it's not perfectly visible, but it's a bit under predicted. Although like basically the mean squared errors are again quite good. Also for this case. And what we now see is that in the global domain decomposition approach, the solution now converges, not to the threshold I set, but to another a bit higher threshold, but it's still in the regime of 2 to the power minus 5, so it's okay. And then it stagnates. But what we now see here is that it's kind of under predicted. So we do not reach the maximum value as in the ground truth. So what our primary conclusions are now, first, that the flow dynamics are predominantly governed by the X component. So the Y component is significantly smaller magnitude, also depending on the specific geometry. So if it's only a channel, the Y component is 0. But if it's like more stenosed, it gets also bigger. But that makes also like the Y component more challenging to learn. Yeah. And the original Takashi approach showed for this example an unstable convergence behavior, although on the local subdomains the predictions were quite good. I also tried it for using a different epoch number, where I saw that it was kind of a bit under predicted. Then it did not, it converged, but also to a wrong solution, again to an under predicted solution. But yeah, so these were my findings. And the global solution is, again, strongly dependent on the local subdomain solution, which makes sense because we only have information at the inlet and basically also at the outlet, but really it has to propagate to all the subdomains. And small under or over estimations amplify errors. But so our result is that the hybrid approach is most promising with a certain input width larger than 1, because it leveraged additional spatial information. And in all my test case, it did not show unstable convergence behavior. So what I now tried out is another loss function, which is a weighted loss function, where we compute the loss function for the velocity X component and velocity Y component separately, and then weight by the standard deviation obtained from the training data. And this helps to assess kind of the scale differences in the X and Y, in the X and Y component. So this was our hope. So the only difference is now we use this weighted mean squared error loss function with this standard deviation values as factors. And what we here see that the prediction on subdomain is pretty good, and also the domain decomposition approach converges. So we see here, this is really good locally. Local prediction is good. Also for this subdomain, And what we nicely see is now when we have good local subdomain predictions, the global domain decomposition loop also converges after, with here not to the certain threshold I set, but to another threshold and then stagnates. So I ran many other iterations, but it always stayed constant to this value. And so this shows really if they are good enough, it also the global approach can converge. And this is also visualization of the absolute error and the relative error. And we see it's really here low for the X component, and for the Y component, this is higher because, as I said, it's basically zero, the Y component here. So now conclusion and future outlook. So the assumption which we first made for all these approaches were a steady state flow, constant material properties, a fixed image size that covers the entire artery geometry in Y direction, but which is kind of reasonable because the geometry varies mostly in X direction. So it's a reasonable assumption to first say it covers the whole Y direction, so the whole cross section. Then we fixed also maximum diameter equals to the inlet and outlet diameter. So there is the geometry is always inside the union of all the subdomain images. And we set this trick where we set directly boundary condition at global inlet and outlet if there is enough long enough channel inlet and outlet region. And the main challenges of this approach for this realistic case are now first the local subdomain solution. So as the velocity information are only available at the inlet and outlet, the error really propagates inside and amplifies. So we really have to have good local subdomain predictions. Then the problems also like the scale difference with the Y component. And also what we have to keep in mind that in this approach, currently no physics is introduced. So mass conservation is not fulfilled. So the mass can either vanish or multiply. And now improvement approach, further steps is first what I observed now also generating the data was that for the same experimental setup, the training history kind of sometimes differ. And I think it's due to non-deterministic GPU operation or other non-deterministic operations. And this kind of changed also the results. At some point it worked, I had a good local prediction, then I did again, it was a bit bad. So maybe now in this setup, I either run it sequentially or enforce a deterministic behavior to always get the same results, to really explore which approach is the best. And what I will do now also as a first step is to increase the amount of training data, because basically we only have 4,000 images, it's not so much. So maybe already increasing the training data, improve the sub-image prediction, and we have better results. But it's good to have kind of all the other aspects in mind. So for example, architecturally, we thought about training two separate CNNs for X and Y velocity component because they are so different in their nature. It's also already implemented and I also already tested it, but the best result was what I showed you before. But again, you can try out, it's good if it's implemented. And the third aspect is adding physics. So adding a divergence free constant as penalty term and loss function, which is also already implemented, but did not lead at this moment to much better results. And what is really, I think, beneficial, or we think is beneficial, is to introduce the mean flow rate into the CNN prediction. As we know, the mean flow rate is for each cross section, it's constant and it's known. So we could predict it in the CNN and then add it in a loss term, the difference to the known mean flow rate. And also providing the mean flow rate to each subdomain could be interpreted as a simple second level approach, as we already give each subdomain kind of a global information. And if all these things are implemented and kind of evaluated, which is also leads to good results, the next step would be evaluate the performance of the model for all grids. So I only now show you results for one specific grid, but evaluate for all grids to show how many converge, how many diverge, and how large is the error. Then also test the numeric scalability, because basically we could just add inside many subdomains. We could just extend the geometry, but then we have to kind of look how the error evolves if we do longer and longer channels. And also, compare and analyze more what is the best experimental setup. And I want to thank for all the computational resources, the data, and the funding I also received by my graduate school. And thank you for your attention.
Okay, so please start your talk.
Hi, can you hear me? Okay. Okay. And first of all, I'd like to thank the organizers for giving me an opportunity to talk here. I'm Yuki Nagai from the University of Tokyo, the Information Technology Center. And today I'm talking about machine learning molecular dynamics. And I'm developing the method to do the accurate and efficient molecular dynamics, machine learning molecular dynamics. First, I would like to introduce me. And I was born in Hokkaido, and I got a PhD in the University of Tokyo. And I'm a condensed matter theorist. I'm studying the condensed matter theory, and I'm studying superconductivity and also material science. And from 2016, I will start studying the machine learning and physics. Okay. And this is the outline. First, I'm talking about the machine learning and physics. And next time, talking about the self-learning Monte Carlo, which is my method. And I will show the examples. And if I have time, I'd like to show the recent works, SLHMC mix, which was published in the Journal of Chemical Physics, I think last November. Okay, so I think, as you might know, but I'd like to introduce the machine learning. And as you might know, there are many applications, for example, image recognition, AI chat, or other picture generations. And I think the important point is that usually we do not have a theory of this. For example, if we have many pictures of cats and dogs, then if you want to recognize whether there is a cat or not, cat or a dog, I mean that there is a cat or not, then we have some input data, pictures of cats, A, and B is output, there is a cat or not. Usually we do not have a theory, concrete theory, but if we have many data, we can build the machine. So I think in many cases, we do not have a theory, but in the simulations, we have a concrete theory usually. For example, if you want to simulate something about, for example, the hydrodynamics or quantum mechanics, or we have a theory, for example, the Navier-Stokes equations or Schrödinger equations. So the input is usually the atomic positions or fluid density or other physical values. And output is usually some kinds of the energies or some densities or other velocities distributions. So, but usually the computational cost is very heavy. So we want to replace the heavy computational cost by the effective model, so-called usually surrogate model in, I think, engineering field. So, and this is my concept. I mean that I would like to speed up the simulation with machine learning by replacing the heavy computational part by the machine learning model. So what is machine learning? I think you might know, but I'd like to explain this. As I said, for example, if there are many cats and sometimes dogs, then this is regarded as input vector X, and the output is in this slide of Y. Y is yes or no, cat or not. Then we want to build the function F. So if we have the function F of X, we can predict the result. For example, if we consider other cats, then we can recognize this is cat or not. And in terms of the machine learning molecular dynamics, the input is the atomic positions, and the output is energy. So we want to replace this heavy computational cost. I mean that in this slide, this purple square is sometimes this is a density functional theory calculations or other heavy computational method with the quantum effect. But now we want to replace this part by the machine learning model. Okay, so I'd like to explain the relationship between the physics and machine learning. I think these are similar because what physicists do is that we usually observe the phenomena and we build some kind of concrete theory, then we can predict what happens. And in the case of the machine learning, also we gather data. This means that we observe something. Then if we have many data, we can build some function f, then we can predict what happens. So these are very similar. So which means that we can easily apply the machine learning method to the physics. And the important and efficient method is machine learning molecular dynamics. So as you might know, virus, DNA, materials, human, animal, Earth, sun, galaxy, everything is constructed by atoms. So if we can simulate dynamics of atomic motions, we can simulate everything in the world. But of course, as you know, the computational cost is very heavy. But if we know the interatomic forces, we can calculate this kind of time evolutions. And the forces can be usually calculated from the energy. So we want to obtain the accurate forces. Then we have to calculate the accurate energy. So the accurate energy is usually obtained from the accurate calculation, so-called density function theory or other first principle calculations, which have the quantum effect of the electrons. But this is very heavy. But if we can do the highly accurate molecular dynamics, there are many benefits because we can design materials, batteries, medicines, etc. by screening of candidate materials by simulations. For example, if we consider to find new batteries, what kind of atom is good for good ion conductivity? But of course, this is very heavy usually. So there is a new method with the machine learning. This is so-called machine learning molecular dynamics. The machine learning model can imitate heavy computational cost with quantum effect. Sometimes it takes 1,000 times faster. This means that it takes, for example, it takes 3 years per one candidate. It becomes 1 day per one candidate. Then this means that if we have 10 candidates, if you have supercomputer, I mean that if you submit 10 jobs in the supercomputer, it takes only 1 day for 10 candidates. So this is very fast. So usually now the machine learning molecular dynamics is used in the university and companies or other many fields, I think. So I would like to explain the machine learning molecular dynamics. The important paper was published in 2007. I think this is old paper now. And the important point is that input of the neural network is the atomic positions, and the output is energy. So we want to replace the DFT calculation. DFT means the density functional theory calculations. Then if we have some machine learning model constructed by the neural networks, it takes 1,000 times faster. The important point is that usually we consider the environment of some specific atom. Then we build some neural networks. And the important point is that in physics, the same species means the same atoms. I mean that we cannot distinguish two, for example, the hydrogens. So this means that neural networks should be same. So we use the neural networks, the same neural network in same species. So with the use of these conditions, we can successfully build the machine learning model. For example, if we have many atoms, we can easily apply the machine learning molecular dynamics. So I'd like to show the examples. I calculated the atomic motions of the aluminum 396, lithium 68, palladium 880. This is very complex systems. And the important point is that there are 4,000 atoms in this figure. And for example, if we have some 30,000 atoms, you can do the simulation with DFT accuracy. I mean that we can include the quantum effect. And in this case, it takes 30 seconds per one step with 20 CPU cores. And the important point is that computational time is proportional to 1/cores. So if you have many cores, then you can speed up simulation with use of the machine learning potential. And I'd like to note that if you use the DFT calculation, I mean the original calculations, the computational time is not proportional to the 1/cores. sometimes the 400 or 500 CPU is the limit to parallelize, to do the parallel computations. So this is very good method to use the supercomputers. Then I'd like to explain the self-learning Monte Carlo. I'd like to tell the problems in machine learning MD. The problem is gathering the data, training data. So for example, if we have two kinds of methods to gather data, one is making structures as many as possible by compressing or expanding. Or if you do the first principle calculation, molecular dynamics calculation to gather data. But the important point is that how do we conclude that the number of the training data is enough or not? 1,000, 10,000, or 100,000? And we do not know because accuracy might be improved with including some much data, but we do not know. So this is an important point. So now to avoid this problem, we introduced the Markov chain Monte Carlo. The Markov chain Monte Carlo, MCMC, is widely used to integrate some functional in high-dimensional space. So there are many applications such as Bayesian statistics, computational physics, quantum chemistry, and quantum biology, etc. The important point is that to use with the use of the MCMC, we can overcome the problems of the gathering data problem. So there are two purposes with use of the MCMC. I mean self-learning Monte Carlo, SLMC. So there are two purposes. One is to obtain the exact MCMC simulation with machine learning. Usually, if you use the machine learning model, of course, this is surrogate model. This means that results should be different because this is not original model. So, for example, if we consider the input data A, then we have some output data B with use of the original calculations. But if you use the effective model, even if the input is same A, but output is B prime, which is different from B. So this means that if the efficient model is not good, B prime is not good, of course. So how long do you have to train this model? Because if you have infinity time, you might have some exact result, but usually we don't have time. And also there is a limitation of the neural networks. So we want to avoid this kind of problem. By using the self-learning Monte Carlo method, the output with the effective model becomes exact. So this is good properties. This means that output should be B, not B prime. And second purpose is to build highly accurate machine learning model. For example, if you want to do the real-time simulation, for example, molecular dynamics, with very heavy computational costs, so usually then you want to build a machine learning model. But the important point is that how accurate this model. I mean that if you have some trained model, so now we want to do the simulation with this model, but result is good or not, I don't know. And to know the accuracy, you have to do the original simulation, but sometimes it takes much time. So to avoid this, to overcome this problem, with use of the self-learning Monte Carlo, you can train the effective model efficiently. So there are two purposes. So what is the self-learning Monte Carlo? I'd like to say that in the common simulation with machine learning, first you gather data and you train the model. Then after obtain the good model, you do the simulations. I mean that you evaluate the model. If the model is not good, we gather more data. Then go back to gathering data section, and again, you can have some good model. But in the case of the self-learning Monte Carlo method, in the same simulations, we gather data, we train the model, and also we evaluate the model. So in the same simulations, we can have good model. This means that number of training data is drastically reduced, for example. Okay, and this is self-learning. This is one of the Markov chain Monte Carlo method. So we can apply this method to various kinds of fields. For example, in spin systems, electron systems, and atom and molecule systems. Also, the lattice QCD system. Lattice QCD is a quantum Cologne dynamics, which is a high energy theory. So SUN engaged theory. The important point is that we can apply this method to various kinds of fields. So if you have some molecular MCMC problems, you can use this self-learning Monte Carlo. So now I'm talking about the detail of the self-learning Monte Carlo method. There are two kinds of SLMC. One is SLMC, self-learning Monte Carlo method. The other is self-learning hybrid Monte Carlo method. So the important point is that we use the machine learning model to propose new configurations. In the self-learning Monte Carlo method, and this is the Markov chain Monte Carlo method. So can you see the pointer? No? Okay, so this is black, so sorry. Okay, but the left side, and there C1, C2, CA, CB is the configuration of the MCMC, Markov chains. And now we want to propose new configuration from CA. This means the new configuration is, for example, CB. To propose new configurations, we use another Markov chain with probability W prime. W prime is the probability of the effective model. Then we can have some proposal configurations. Then we do the acceptance or rejected test with the use of the metabolic testing test. Then if this proposal is accepted, we use these configurations. Then we can do the simulation. The important point is that we use the machine learning model only in the proposing sections. So this means that accuracy is determined by the original Markov chains. This means that result is exact. And in the right side, in the SLHMC, we use molecular dynamics to propose new configurations. So these two are very similar. So I mean that the left side, we use another Markov chain. In the right side, we use machine learning molecular dynamics to propose new configurations. So I'd like to say that the machine learning techniques are used for only proposing new configurations. And I'd like to say the concept of the SLMC and detail. I mean that acceptance ratio for the conventional metabolic testing algorithm is this one. So there are W is the weight and probability, and Z is proposal probability. And with the use of another Markov chain to propose new configurations, this G becomes W prime because this is Markov chain Monte Carlo. Markov chain Monte Carlo means that we generate some kinds of probability distributions. So the G is proposal probability, which means that proposal probability is equal to the W prime. Then the acceptance ratio is written as this form. And we have W prime and W. Then if W prime is equal to W, then the acceptance ratio is 1. So this is high acceptance ratio. And the important point is that if the computational cost of the proposal Markov chain is small, we can speed up the simulations. Then to build the effective model, we use machine learning techniques. And I'd like to explain the SLHMC. This is very similar. We use molecular dynamics to propose new configurations. The acceptance ratio for the metabolic testing algorithm in hybrid Monte Carlo is this. The ratio of WCB and W to CA. And there is no W prime dependence because there is a time reversal. The MD is time reversal operations. The important point is that if the computational cost of the MLMD is small, we can speed up the simulations. Okay. And now I'd like to talk about the self-learning hybrid Monte Carlo method. First, we do some kind of original calculations. Sometimes this is the DFT calculations. Then we have the input, the atomic positions, output, the energy. So we can regard this training data. Then we do the molecular dynamics, MD, machine learning MD, to move the atoms. Then we have some different atomic positions. Then we calculate the original calculation, I mean the DFT calculations, we obtain the new data, new training data. And so on, we have many data. For example, if we have 100 training data, we retrain the new models. Then we put this new model to this molecular dynamics part in the same simulations. This means that the machine learning model is automatically improved. So this is on-the-fly improvement. And data is gathered in a target ensemble because this is just a Markov chain Monte Carlo. Okay. And I would like to show the difference between the molecular dynamics. And if you use the first principle molecular dynamics, the accuracy is very high, and also computation cost is very high. And if you use a machine learning MD, and accuracy is similar to first principle MD, and the computation cost is low. And with the use of the SLHMC, the accuracy is same as the first principle results, but the computational cost is middle, because now we use DFT calculations, original calculations. But in the case of the machine learning MD, there is no original calculation. So computational cost is lower in the case of the machine learning MD. But the important point is that there are two purposes. One is that if you want to do the simulation with exact accuracy in the DFT level in the system, that's the DFT MD is not too heavy to use. I mean that if you want to consider the large systems, then we cannot calculate these simulations. Then with the use of the SLHMC, you can have exact results. And if you want to construct accurate neural networks for machine learning MD, you can use the SLHMC because the machine learning model is automatically improved. So in both cases, neural networks are automatically optimized. Okay. And I would like to show the examples. First, this is trained by run. I said trained by run. This means that we train the model and we measure the physical observables. So this is a vertical axis is a number of DFT calculations. Horizontal axis is the number of DFT calculations. Vertical axis is accuracy. Every 100 times steps, we train the model. The important point is that we can obtain the good result, and also we can get the accurate model. This means that this is just a Markov chain Monte Carlo, so the accuracy should be same. So now I confirmed. And the important point is that if the MD part becomes longer and longer, then the auto-correction time becomes shorter and shorter. So if we use the longer molecular dynamics, we can easily cut the correlations. I mean that auto-correlations. Okay. And next, I'd like to show the train and learn case. I mean that first we train the model, then we do the MLMD, molecular dynamics. So this model is complicated, but I would like to say that this is a phonon-mediated unconventional SF superconductor, and this means that phonon is very important. So now I wanted to know the energy dependence of phonons. So then we train the molecular dynamics, machine learning potentials, and then with use of these converged models, we do the machine learning molecular dynamics. Then we have some results. The important point is that we can easily do these simulations in same. I mean that we can easily do the simulation. And I would like to show the elapsed time. The left-hand side, we train the model, and also we measure the physical observables. The left is original calculations. This means that 800 hours in say one simulation. But if we use the SLHMC, this becomes 30 hours with including the training time. So this is very fast. And now we use 240 CPU cores in the supercomputer of the Japan Atomic Energy Agency. And the right-hand side, the original calculation, it takes I think 3,000 hours. But if you use the SLMC plus, I mean the SLMC and molecular dynamics, it takes only 30 hours, I think. Then that SLHMC is very fast to train the model and also to get the physical observables. And I would like to show another case. I mean that we developed the SLHMC for NPT ensemble. NPT means that constant pressure, constant temperature, and constant number. And I would like to say that if the model is bad, usually MLMD breaks down. So in this case, we consider the some model trained with 8,600 structures. But with use of this model in the molecular dynamic, I mean the machine learning MD, the result is broken like this MLMD case. The crystal structure is broken. But with the use of the SLHMC, this is very stable because the bad structure is rejected in the simulations. And I would like to show some results. I mean that the calculation becomes exact, and we can see some kinds of the time dependence, and also we can compare the experiments. So with the use of the SLHMC, we can do the simulations where the original calculation cannot be applied. Okay, now I'm talking about the recent works. And there is a problem with SHMC. And for example, if you have bad model, for example, in early stage of simulation, we do not have a good model. Then the bad model cannot be accepted in early stage of simulation. So for example, we use short MD steps because if the MD step is very short, the structure is very similar to each other. So then we can accept this proposal. But sometimes it is not good. So now how to improve acceptance ratio? So now we propose a new method, SLHMC mix, in this paper. The important point is that acceptance is in the SLHMC, the acceptance ratio is a ratio of the original model, W, and the weight. But with the use of mix, SLHMC mix method, we use W and W prime. I mean that the weight of the original model and the weight of the effective model. Then we can improve the acceptance ratio. Of course, the ensemble should be changed. So now with use of SHMC, first, before showing the result, I would like to explain the path integral energy, because if we want to simulate the water molecules, we have to consider the quantum effect. I mean that quantum effect of atoms. So there is 0-point oscillations. So we have to consider some kinds of quantum effect with use of path integral method. But sometimes this computational cost is very heavy. So we cannot do this simulation in larger cell. But with the use of SLHMC, we can do this. So this is a result of and if you are interested in the work, please see this paper. I just show the brief summary. The important point is that with use of the reweighting techniques and modified acceptance ratio equations, we can obtain the exact result. And if with the use of this method, we can consider the which choice of the exchange correlation functional is good or not. This is very important because in water molecules, for water molecules, the choice of the exchange correlation functional in the original calculation is very important. But the computation cost is very heavy in the water case with use of the path integral method. So sometimes this cannot be done. But with the use of this, the cost becomes 1/20. So we can calculate these kinds of differences. So I'd like to summarize my talk. I'd like to introduce the self-learning hybrid Monte Carlo method. There are two properties. One is the exact method, because this is a Monte Carlo method, and this is on-the-fly method. So this means that the machine learning model is automatically improved in the same simulations. So if you can use the SLHMC when you want to do simulation with exact accuracy, or you want to construct accurate neural networks for machine learning MD, it is very good to use SLHMC. And this SLHMC was already implemented in the open source package PRMD. So if you search this word PRMD, you can get this software, and you can easily do the machine learning molecular dynamics or SLHMC. Thank you for your attention.
So okay, so that is all the talk is finished, and so thank you very much attending this seminar, and I hope that this talk is help you for this discovery a new research topic. Thank you very much for coming today. Now closing. どうもありがとうございました。これで終わりたいと思います。